So hi, welcome. So today we are going to talk about some applications of Laplace transforms. One example in the application is called for ODEs, ordinary differential equations for time-varying problems. Okay, so for example, you have y double prime plus 2y prime plus y equals to, let's say, sine omega t. Okay, it's a spring mass dashpot system. Okay, so how do you solve this ODE? You can use Laplace transforms. Okay, so of time varying systems. Laplace transforms are actually good for systems like these. These are called linear time invariant (LTI) systems. What is a linear system? Linear system, that means, okay, if I have y double prime is d2y dt squared. I don't have any of these y double prime, y prime, and y terms. I don't have a square or square root or any one of them. So for example, non-linear will be something like this. Okay, non-linear will be something like this. Okay, if I have y double prime squared, this will not be a linear ODE. So Laplace transform won't be as powerful over here. You may need to think of something else. Okay, another way to solve this system. But if you want to solve this kind of ODE, very easy with Laplace transform. So what am I talking about here? Why is it easy? You know, if you want to solve second order ODEs, you probably have to think about thinking about the homogeneous part, and then you think about the particular part. Alright, and if you want to solve a first order ODE, right, something like this, y prime plus 3y equals to some exponential minus at. Okay, or y prime plus 3y equals exponential at plus 4, something like that. Okay, exponential of 2t plus 4. How are you going to solve this kind of thing? Okay, so or even y prime plus 3y equals to 4. Okay, so what you need to think of is this thing called the integrating factor. And if you're not fond of using integrating factor, you can just do Laplace transforms. Okay, of course you need boundary conditions to solve these two ODEs, but we'll just leave that out for the time being. Okay, so these are linear systems. What about this thing called time invariant? Okay, time invariant means the ODE does not change with time. So let's say t equals 1, the ODE is this form equation. Then maybe at t equals to 100, you have an ODE change to this form. That is not a linear time invariant system. Because with as time changes, your ODE also changes. So well, that doesn't work. Okay, so all of this seems very abstract for now. Maybe we can talk. Yeah, it seems very abstract for now, but we'll just learn the math bit first, and then we'll see what other things we have later. So let's just solve these ODEs. Okay, we have the second order ODE first. Okay, so what generally we do is to just take the Laplace transform of this ODE, and then we kind of combine things together, and yeah, you'll see what I mean. Okay, so first step, take the Laplace transform of the ODE. Okay, Laplace transform of y double prime plus 2y prime plus y. Okay, and that will equals to the Laplace transform of sine omega t. Now, good thing about this sine omega t, we already derived the Laplace transform just now. So what's the Laplace transform of sine omega t? Okay, I mean, of course, you can look up in tables on the internet. Okay, sine omega t, the Laplace transform is just omega over omega squared plus s squared. So omega s squared plus omega squared. So that's very easy. Okay, and the first and second first order derivative and y, well, Laplace transform of y, well, we'll just call it y of s, right? We'll just call it y of s. Okay, we have y of s plus 2. Well, remember we also derived the way to do partial differential. I mean, we also derived the way to do what do you call it? Differentiated ODEs. I mean, we learned how to do Laplace transform of derivatives. That's what I'm trying to say. So we did Laplace transform of ODEs as well. Okay, so what's the Laplace transform of not ODE? Laplace transform of derivatives. So what's the Laplace transform of derivatives? Okay, s times the Laplace transform of the f of t, which is just y of s, minus, okay, we'll just get y at t equals to 0. Okay, y at t equals to 0. Okay, now, okay, so that's one part. Okay, all right. So, what else? What else do we need to do? Okay, we also need this third one. This Laplace transform of this second order derivative. Okay, so that's what we'll do now. What's the Laplace transform of the second order derivative? Okay, so if we integrate it once, it'll be sy prime s, or s times the Laplace transform of, okay, f prime t, or y prime of t, minus y prime at t equals to 0. Okay, so now you need more and your other boundary condition. Okay, so pardon the cracking of knuckles. Yeah. Okay, so what's this Laplace of y of t? We can actually just substitute the whole thing here. Okay, s y of s minus y of t equals to 0. Okay, and this is how you do your second order derivative Laplace transform. Okay, s squared, s will be here. Alright, so y at t equals to 0 and y prime at t equals to 0, both of these are constant. These are boundary conditions you may need to set later on. Okay, so I'm not going to include the boundary conditions now, but I will just leave it as it is inside the question, or inside the solution, so to speak. So I mean, yeah, that's it. So we can actually just substitute this back here into this Laplace transform here. Okay, you just substitute it back into this Laplace transform here, and then we will actually move all the sy t equals to 0, y prime t equals to 0, y t equals to 0, all of it will move it to the right hand side. Why? Because then we can factorize out this y of s. Okay, so we can just move it all to the right hand side. So I have this 1 plus y prime t equals to 0, y prime t equals to 0 here. Okay, so we have s squared ys, y of s, and we remove these two terms to the right hand side. I'm going to start multiplying all of this in. Okay, I'm going to multiply all of this in, and I'm going to bring the term 2yt equals 0 to the right hand side. Okay, 2yt equals 0 to the right hand side. Alright, so just note that this yt equals to 0, y prime t equals to 0, and 2yt equals to 0, all of these are constants. Of course, you can actually factorize out yt equals to 0 together just to make things a little bit neater. So we'll just do that. 2 plus s. And that's how we will get this this part here. Now thing is this, okay, we will factorize out y of s, and then we will y of s, and then we will have s squared plus, okay, s squared plus 2s, s squared plus 2s plus 1. Okay, s squared plus 2s plus 1. Alright, so we'll just bring all of this to the right hand side. Okay, so it's very simple. Okay, and then we will just do this inside the right hand side. Okay, I need a fraction here. 1 over s squared plus 2s plus 1. And of course, I'll put all of this into the numerator. Okay. So let's see how much time I have left. Okay, still quite a fair bit of time. Okay, so now I will just, for the sake of neatness, I will just factorize these two out. I'll put these two in different terms. Okay, so I will have a plus fraction, okay, y prime t equals to 0. Y prime t equals to 0. Now I have this s squared 2s plus 1. Okay. Alright, so this thing here, we can just inverse Laplace transform. This thing you can also inverse Laplace transform. And basically all of these things you can just do the inverse Laplace transform, so we can find y of t. Okay, so y of t equals to mathcal O or mathcal L. Then this time we need to do an inverse Laplace transform of all of these terms inside here. Okay, now inverse Laplace transform, there is an analytical way to do it, meaning to say there is a formula for it, and then you kind of do it by hand, but we're not going to do that. Okay, we're going to save ourselves some trouble. Okay, and we'll try to do things the easier way. Okay, we'll try to do things the easier way. Okay, so you know the thing is that we have all of these formulas that we just derived. Okay, the cosine, sines, and exponentials. Okay, and we take a look at the form of these exponentials. So basically, we can break all of these up into sines, cosines, and exponentials. How do we do that? Okay, so I think this example is convenient enough. You can see in this denominator here we have s squared plus 2s plus 1. This is actually just s plus 1 squared, right? S plus 1 squared. And what is s1, the Laplace transform of e to the minus t? That is just actually s plus 1, or 1 over s plus 1. Okay? So basically this thing here, okay, we can actually break it up into two partial fractions. Okay, we can actually break it up into two partial fractions. So okay, so I'll just give you a note here. Laplace transform of e to the minus t equals to 1. Okay, not 1. Oh, 1 over s plus 1. Okay, let me put the brackets in so that's neater. So what can we do? We can break up both of these fractions. Okay, we can break up both of these into partial fractions. Now, again with partial fractions, yeah, I'm not going to do a full derivation here. I'm definitely not going to do a full derivation. But basically, the idea is we can split all of these up into partial fractions, and then we see how they, sort of correlate to our sines, cosines, and exponentials. So, okay, so we'll have to do some partial fractions, especially on this first one. The second and the third term, we'll talk about how to deal with them later, especially this 1 over 1 plus s, 1 over s plus 1 squared. Okay, there's a property that we need to use. It's called frequency shifting. Okay, so let's talk about this first term first. How do we do this partial fraction? So we do the partial fraction. Alright, and I'm going to use Wolfram, alright? I'm not going to solve it. I'm going to use Wolfram for it because I don't want to do the partial fractions bit. Yeah. Okay, because very, very tedious. Okay, so this is a repeated linear factor kind of a thing. So this is a x squared plus yeah x squared plus omega squared, s squared plus omega squared. Then there's a repeated linear factor. So usually, okay, concept is this, right? Concept is this. You'll have a bs plus c s squared plus omega squared. Then you'll have a fraction, maybe something I call d s plus 1 plus fraction e over s plus 1 s plus 1 squared. So you cannot really do a partial fraction over s plus 1 squared, but these are the rough denominators you should expect. Now, notice here, if you actually expand these out into, of course you can multiply that back in, and then you'll find your b, c, d, and e. Okay, where these are constants. Okay, b, c, d, e, and e are constants. Okay, so if you actually notice, you will have s squared plus omega squared. These are actually this s over s squared plus omega squared. These are sine and cosine waves. You see, bs over s squared plus omega squared, c over s squared plus omega squared. These are sine waves. And d over s plus 1, e over s plus 1 squared. This one you can see is an exponentially decaying curve. This one, okay, we haven't quite derived it yet, so we'll need to talk about how to derive it. But let's at least find what b, c, d, and e are. Then we talk about deriving this s plus 1 squared. Okay. Okay, so I'm just gonna take Wolfram. Okay. And I'll just leave it here. It's a little messy, but this is what it looks like. Very messy, yeah. So we have 2a over a squared plus b squared. Yeah, I do partial fraction of this. 1 over x plus a squared, x plus b squared. Well, a here is actually 1. I can just make it simple for ourselves. Only b here. B is omega. B is omega. So yeah. So let's just copy this down from Wolfram. Okay. So I don't want to do everything. Okay. So fraction, there'll be, okay, I'll put 1 over here. So every time you see b here, there'll be an omega. So I need a minus omega squared minus 2s plus 1. Okay, minus omega squared minus 2s plus 1. Okay, minus omega squared minus 2s plus 1 over omega squared plus 1 squared. Okay, so I'll need a omega squared plus 1. This whole thing is squared. And don't worry, this is actually, all of these are constants. Okay, and then you have omega squared plus s squared. 1 over omega squared plus s squared. Alright, so there are a fair bit of constants here. Omega is a constant, so don't let that worry you. Okay, basically we can reduce this whole signal here into sines and cosines. That's the first part. Second one is this one, 2 over b squared plus 1 plus 2 over b squared, which is omega squared plus 1. Okay, then we have an exponential decay curve. Okay, 1 over x plus 1. Fraction 1 over x plus 1. Or s plus 1, sorry, s plus 1. Okay, that's the second part. So this thing in front here is a constant, which is what this d is supposed to be. Now for e, very simple. 1 over b squared plus 1, which is 1 over omega squared plus 1. Save 1 over omega squared plus 1. And then 1 over x plus 1. 1 over s plus 1 squared. S plus 1 squared. Alright, so we have this term here, this term here. All looks very messy, right? Okay, I'll just do it this way. Okay, we will have let's see, we'll have c. Yeah. Okay, okay, e, right? E equals to omega, fraction of omega. Okay, omega over omega squared plus 1. Okay, so that makes it a lot neater because I need to multiply omega throughout, right? So that's going to be e, omega over omega squared plus 1. Okay, all right. Never mind. Let's multiply omega. Then I will have this omega, and then I will have to multiply that throughout. Okay, it's somewhat tedious, but yeah, it's not always there. Like I said, not always easy, especially now with the partial fractions part. But it does prevent you from needing to do all this guesswork of like variation by parameters and everything like that. Okay, so omega is here, and omega is here. So omega over omega squared plus s squared, there's a sine slash cosine kind of a wave. Alright, so great. Okay, so let's deal with e first. D will be this. D equals to 2 omega over omega squared plus 1. That's D. And this whole thing here will be the bs plus c, alright, so to speak. So yeah, let's do it. What's the coefficient of s? Or what's the coefficient of s here? So it's 2 minus 2. B equals to fraction minus 2 over omega square plus 1, and the whole thing will be squared. Okay, hopefully you can see that. This will be here, and yeah, of course you actually need to multiply in the omega. And then what is c? Okay, c is depending on whether omega changes, c will also change in value. So c is actually omega. Okay, 1 minus omega squared. Okay, 1 minus omega squared over this whole denominator here. So all of this really depends on the frequency of the sine wave you are setting in, which does make sense. The behavior of the system which is mentioned over here, it will depend on the frequency of the sine wave that you are sending in. Okay. That's quite fundamental as well if you talk about frequency response. Alright, so hopefully that cleans this whole equation up. So we can reduce the first term to this. Okay, I think there's a careless mistake here from I just saw. This should be omega squared plus 1 whole thing squared. Because that's what it says here. B squared plus 1 whole thing squared. So from Wolfram, okay, the second one will need to be squared. Okay. Okay, so compile this, let's see, and multiply by omega. Okay, and let's put by omega here, and of course lastly we'll need to change what D is. Alright, okay, I think now we're on the right track. Yeah. Okay, so that's more or less what it's supposed to be. Okay, B is 2 omega. All of these are really dependent on omega. Okay. So of course if omega equals 0, all of these things will just drop out. All these terms will kind of just drop out. Then we'll get a different sort of response there. Okay, so it reduces the first term to this, which is a combination of sine and cosine signals here with this characteristic, it may be a different characteristic frequency, okay, depending on what you have here, but they are just a superposition of sine and cosines. You can actually combine them together. You might actually find that, and I believe you'll actually find that you will have a sine signal with the same frequency but a phase shift, something called a phase shift. Okay, so that's very common in frequency response. These two will actually be some exponential signals, but this e over s plus 1 squared, this is not just exponential signal. There's a t in there somewhere. Okay, likewise this thing also we can reduce the two the same way, but for now I think we'll stop. It's long enough video. I'll just take a break and maybe I'll continue next time to solve this ODE. Okay, just note that the work here is a lot to do with partial fractions and Laplace transforms. That's it. Okay, thanks for watching.